So welcome along, ladies and gentlemen, to your weekly SETI seminar series. Today we're very lucky to be joined by Rebekah Dawson, who's come down to us from UC Berkeley. Rebekah did her BA in astrophysics at Wellesley, and then she was part of the SETI REU program in 2007. So that's why she might be a familiar face to many of you. And then she did a PhD at Harvard with Ruth Murray Clay on migration behavior of planetary systems. And she's just recently completed that and moved to UC Berkeley as a Miller Fellow there. Rebekah's published on such topics as the photoeccentric effect, Neptune and the bodies circling Neptune, and inheritance of their eccentricity and other characteristics from their time in the Kuiper belt, misalignment of Beta Pectoris, the paucity of proto-hot Jupiters in supereccentric orbits, and her interests are in extrasolar planets, Kuiper belts, debris disks, dynamics of planetary and satellite systems, signal processing, and astrostatistics. So she's going to cover all those topics in the next hour. So please join in welcoming Becky.
Thank you so much. Is the microphone still working?
Yeah.
Great. So I'm going to be talking about Nature's instruction booklet for planetary migration. But before I tell you about some brand new results about exosolar planets, I want to go back a few hundred years. This is a painting of an orrery, which is a mechanical model of the solar system. And a few hundred years ago, it was a great source of comfort to Enlightenment thinkers how orderly and constant the planet's motions are, how they seem to follow their orbits like clockwork. And more recently, at your kitchen table, you or your children may have made your own model of the solar system and taken satisfaction of putting each planet in its proper place. And you may have thought, this is what a planetary system should look like. But you may have also wondered as you looked out at stars at night whether all of those stars have a planetary system that looks like ours. And it's only in the past couple decades that we've started being able to answer that question. And the answer sometimes is no. This is an artist's depiction of a hot Jupiter, which is a planet that's the size of Jupiter in our solar system, but is orbiting closer to its star than Mercury is to the sun, being heated to thousands of degrees. We don't have anything like this in our solar system. And in fact, of the checking today 763 confirmed exoplanets, most of them have orbits that are nothing like what we see in the solar system. There are hot Jupiters and their smaller cousins, hot super-Earths. There are planets on orbits that are misaligned from their host star's spin axis, planets in special configurations called mean motion resonances where they're exchanging energy with each other. There are planets on very elliptical orbits where over the course of their year, they go from being really close to the star to really distant. And there are even systems that, unlike in our solar system, the planets are not all in the same plane. So these planets don't seem to have formed as we expected, or something happened to them that's different from that constant mechanical motion that you'd expect in a planetary system. And now, instead of taking comfort from a mechanical model or an orrery, when we try to look at these planetary motions, all these thoughts intrude about the extrasolar planets that have been discovered and how their motions don't seem so constant. They seem like something has happened in these systems to shake them up. Even in our own solar system, you may have felt sorry for Pluto when it was demoted from a planet to a dwarf planet, but that's probably not the worst thing to have happened to Pluto. In this sort of old-fashioned picture where Pluto is still considered a planet and is in a picture of the solar system, you can see that it's not orbiting in the same plane as the other planets. It has a very inclined and elliptical orbit. So even in our own solar system, we're seeing some evidence that the planets' orbits have probably changed from that disk that we think that they formed in. When I was recently at IKEA, I realized that planetary systems seem to have something in common with my new futon, which is that like the IKEA furniture in a postdoc's apartment, planetary systems seem to be formed with some assembly required. So today we're going to try to figure out what's written in that assembly IKEA booklet and are these instructions for putting together a planetary system involve gentle processes or violent processes? And to do that, I'm going to use two classes of evidence. One are hot Jupiters, which I'd show you the picture of earlier, those really close-in planets that we think are displaced from where they formed. We can also find some evidence around using debris disks, which are leftover material from planet formation. This is a picture where we're looking at a disk edge on. You can see instead of being flat, the disk is warped. That's telling us something about the orbits of the planets in the system. So let's first talk about hot Jupiters. We think that giant planets form on circular orbits out of a disk of gas and dust. And we think they form beyond the ice line, so at a distance where it's cold enough that you can get icy materials to make the planet's core, and then accrete a bunch of gas before this gas disk evaporates away. So how does a planet get from being at Jupiter's location to being as close as a hot Jupiter? Or another way to look at this is, how do we take Jupiter's orbit and shrink it by a factor of 100? There are basically two classes of theory for trying to do this that people have proposed. One is gentle disk migration, where the disk that the planet forms at exchanges energy and angular momentum with the planet and causes it to move in to be very close to the star. And this is the way that IKEA recommends forming planetary systems. But then there's the less IKEA recommended way, which is that you can have the different planets or stars in the system gravitationally interacting with each other, and this can perturb their orbits. So let me show you what sort of evolution we expect for the Jupiter's orbit in these two different types of theories that people work on. With disk migration, the planet starts out on a circular orbit like we think it's formed. It's far away from the star, and the disk that it forms from is still around, so it's exchanging energy and angular momentum with the disk, and it's just very smoothly moving in. It's staying on a very circular orbit until it eventually gets as close to the star as a hot Jupiter. So then let's think about how the other type of theory I mentioned can lead to a hot Jupiter. Again, you start out on a very circular orbit, but now some other body in the system perturbs the Jupiter and makes its orbit become very elliptical. So now the Jupiter is getting very close to the host star during part of its orbit, and the host star is basically trying to pull it apart, and it doesn't succeed, but in this process known as tides, the planet is going to dissipate a lot of its energy. So as the planet is experiencing this tidal dissipation, it's going to go from this very eccentric orbit to a smaller circular orbit, as we see for a hot Jupiter. So that's the other way to do it, and we'd like to distinguish which of these is actually going on in the typical planetary system that has a Jupiter in it. So one way to do that is that there is a prediction by Socrates and collaborators that in the Kepler sample, which I'll talk about in a moment, there should be half a dozen of these super eccentric Jupiters if this is really how hot Jupiters are formed. So we wanted to test this prediction by going out and looking for these super eccentric Jupiters. And to do that, we used the sample from the Kepler mission. So the Kepler spacecraft is monitoring the brightness of a bunch of stars. And as the planet passes in front, as you can see in this little cartoon, the brightness of the star we see drops. And that's how we detect that there's a planet here. And so from this measurement, we can see how big the planet is by how much light it's blocking. And we can know the planet's orbital period, or its year, because we see the planet come in front of the star every orbital period. But the trouble is that this doesn't, at least traditionally, give us a good way to get the planet's eccentricity. So we might see the Jupiter there, but we don't know if it has this super eccentric orbit that we're looking for. So we developed a different approach to try to extract the planet's eccentricity out of this transit light curve. And we call it the photoeccentric effect because the Kepler data is called photometry. It's you're observing light from the star, so it's called photometry, and we're trying to get the eccentricity. So it's a pun on photoelectric effect. Anyway, so the reason that we can hope to measure the planet's eccentricity from its light curve is that a planet transiting on an eccentric orbit is going to be moving at a very different speed than a planet transiting on a circular orbit with the same orbital period. That's because when the planet's close to the star, it's moving really fast, and when it's far away from the star, it's moving much more slowly. So we can see what the difference is in the light curve between the top planet, which is on a circular orbit, and the bottom planet, which is on an eccentric orbit. And you can see from my little cartoon that the shape and duration of this observed transit light curve will be very different for the bottom planet on the eccentric orbit than for the top planet on the circular orbit. So this is somewhat obvious, but in order to actually use this, we have to get around a few degeneracies that you might even be thinking of between, is this really a planet on an eccentric orbit, or is there some other effect that we're not accounting for? So one thing you might be thinking of is maybe it looks like the transit is lasting a really short amount of time, not because the planet's moving fast, but because it's clipping across the top of the star, which doesn't take so long. But you can see from this cartoon that if the planet's clipping across the top of the star, the transit light curve will have a very different shape than if the planet is moving quickly across the center of the star. And the data from the Kepler spacecraft for giant planets is so precise that we can easily distinguish between these two different shapes. So the next few slides are going to be a tiny bit more technical, but I will give you the message from each of those to take home if you don't follow all the technical details. And you can know that we're on these technical slides by this little badge in the corner. If you go to Science Scouts, it's this website, you can get a badge for all sorts of science accomplishments. And there wasn't one for orbital dynamics for some reason. So I used the closest thing, which was the Works with Large Animals Science Scout badge. So once this is gone, then we'll go back to a more general audience talk. But I'm not going to go into great detail. What I just want to show you is how we get around some of these degeneracies. Actually, to go back, you might have been thinking, well, the duration of the transit is going to depend on the size of the star, and the translation between how far it is and between its orbital period using Kepler's law is going to depend on the planet's mass. So what that turns out to be is a degeneracy between the speed of the planet and the host star's density, which is a potential problem because we don't always know the density of the host stars in the Kepler sample all that well. So in the one equation of my talk, what I just want to show you is that on the right-hand side is everything we can measure from the light curve directly. We have the transit depth, we have the timing of the different parts of the transits, we have the planet's orbital period and the universal gravitational constant, which we already know. And then on the left-hand side is what we want to measure. Oops, here's the transit speed, and then next to it is the host star's density. So although these are completely degenerate, you can see that the host star's density is only raised to the first power, and the transit speed is raised to the cubed power. And what that means is that we only need an order of magnitude constraint on the host star's density to know the planet's transit speed. So we can just know, like, okay, this is a star that's pretty much like the sun, has a somewhat similar density, and get the speed pretty accurately to high precision. So the other degeneracy you might be thinking of is, how do we know how the ellipse is oriented? Maybe the planet's going between us and the star when it's on the really fast part of its orbit, but what if it's on the really slow part of its orbit? That's going to be a completely different transit speed. We can't get around that degeneracy, but we can account for it in our final calculation. And that's because of the way that this affects the transit speed. So here I'm plotting on the x-axis is how is the ellipse oriented? Is it facing towards us, going really fast, or a planet far away, going really slow? For curves of different eccentricities, that's how elliptical the orbit is. So we're looking for these really elliptical orbits. So that's like the top two curves. And you can see that for most ways that the ellipse is oriented in space, the planet will be moving at a much faster speed than what we'd expect if it were on a circular orbit. And this lets us easily pick out these planets that we're looking for. The next thing that I want you to notice is, let's imagine that this pink bar is our measurement of the transit speed from the data. And I made it thick because there can be uncertainties in the measurement and also uncertainties in the host star's density. And you can see, first of all, how there's a minimum eccentricity necessary to make this really fast transit speed. So just by seeing a planet zip by really quickly, we know that it must be on an orbit that's at least a minimum amount of eccentric. The next thing is that you can see how tangent that dotted curve lies to the pink line. The pink line is sort of right on top of it. And what that tells us is that the eccentricity is actually more likely to be very close to the minimum eccentricity. And because of that, we don't just get a minimum eccentricity, we actually get a nice constraint on the measurement. So then in the last slightly technical slide, I'm going to show you how we had a really nice test case, which was a planet that had its eccentricity measured through the traditional method of detecting the Doppler motion of the star. And you can see that the dotted lines are the measurements for from that traditional method, and the dark lines are the measurement from our method. And even though we're not really constraining how the ellipse is oriented, what we care about, the eccentricity, we're actually getting a tight measurement that's in good agreement with the more traditional approach. So this is a planet that was discovered by the traditional method and then later found to transit. So it was a nice test case to show that our approach is looking as we think it is. So here's the end of the technical details. And if you didn't follow all of them, I just want you to take away that despite some of the degeneracies you might worry about, we can actually use this to get a measurement of the eccentricity and try to find these really eccentric planets that we're looking for. So how many of these do we actually expect to find in the Kepler sample, and how will they manifest themselves in the data that we're looking at? So this is a plot of the planet's orbital period on the y-axis and the planet's transit speed on the x-axis. And what I want you to take away is that in the dark region is where we expect these super eccentric planets to live. So they should have really fast transit speeds, and they should have long orbital periods. And we expect, based on some calculations that I'm not showing you here, that there should be 5 of these about in the Kepler sample. So this is what we expected to find. Then we went out and measured the eccentricity for all the giant planets that are in the Kepler sample, and let me show you how our results compared to the prediction. So each of these thick bars represents a different giant planet in the Kepler sample. And these bars are thick because there's some uncertainty in the measurements and there's uncertainty in the host star's density. But what you can see is that instead of seeing 5 of these planets in that dark region, we don't see any at all. So what that means is that these super eccentric planets that we expected to find are actually missing in the Kepler data. There is one planet that has a rather high eccentricity. It's called KOI 1474, and there are 2 special things about it. One is that it's on an orbit that is rather eccentric, but it's actually not getting close enough to its host star to end up becoming a hot Jupiter, so we call it a failed hot Jupiter. The other is that when we took all the light curves, all the data, and lined them up according to a constant orbital period, instead of nicely lining up, sometimes the planet is crossing the star too early and sometimes it's coming too late. And this indicates that there's some other body in the system perturbing it. Let me show you a little movie that illustrates that. So you can see there are 2 planets here, and if you watch the inner planet, you can see that it's not going in front of the stars at regular intervals, and that its orbit is actually changing over time because it's getting perturbed by that outer planet. And it's really interesting to find an eccentric planet like this because that outer planet is the smoking gun that could have caused the inner planet's large eccentricity. It may have started out on a circular orbit, but over time, something like this caused its orbit to become eccentric. When we can actually use those, they're called transit timing variations, those changes in the planet's orbital period, to get a 3-dimensional look at the system. And here's what it looks like. You have an inner planet that, here we're looking down on the system. The inner planet's on a highly eccentric orbit, and the outer planet is on a less eccentric orbit, but they're both orbiting in the same plane. And the reason that the planet is sometimes arriving early and late is that the inner planet is spending most of its time far away from the star. So because of that, as the outer planet moves around slowly to different places, the inner planet is feeling a different gravity and orbiting with a different period. But it's actually a little surprising that these planets are both in the same plane, because you might think that if they had some strong scattering event that led to this one being on an eccentric orbit, that it would have also gotten kicked out of the plane. But apparently not. Apparently they're very coplanar, just like the planets in our solar system. So the overall conclusion, though, is that we don't see these 5 super eccentric Jupiters we expected if this is how hot Jupiters are formed. And there are some different explanations for that. Maybe we don't quite understand the process of forming a super eccentric Jupiter as well as we think we did. But it could also indicate that a lot of the hot Jupiters are coming in through the other mechanism, through disk migration. So remember how there's these 2 mechanisms. It could be that they're actually both operating in different planetary systems. And if that's the case, then you might wonder what determines in a given planetary system whether it's going to experience disk migration or whether it's going to have these strong gravitational interactions. And I'm going to propose a hypothesis for what might determine that. So we already know that that there are different types of stars that have different metallicities. So some of them have more solid metals in them than the other ones do, and that this probably correlates with the disks that they formed from. The other thing that we know is that giant planets are much more common around the more metal-rich stars. And the reason people think that this is true is that if you think about that disk that the planet forms from, if there's a lot of solid materials in that disk, then it might be easier to form the giant planet's core and accrete a bunch of gas before that gas disk goes away. So we know giant planets are more common around the more metal-poor stars. So if it's hard to form one giant planet around a metal-poor star, you can think of this like that square. It's like it's not even a planet. It's so hard to form it. Then it's probably going to be hard to form multiple giant planets around around a metal-poor star. So it may be that only the metal-rich stars are more likely to have a bunch of giant planets that can lead to these strong gravitational interactions and cause the Jupiter to go onto that high eccentricity orbit. So the idea is that around both metal-rich and metal-poor stars, a planet can move around through disk migration, but only around the more metal-rich stars are you going to have a bunch of giant planets, or are you going to have this high eccentricity planets and high eccentricity migration. So in support of this hypothesis, I found a few trends in the data that seem to be consistent with this idea, and I'm going to show you just 2 of them. One of them is, so here's a plot where the more eccentric planets are at the bottom of the plot, and then on the x-axis is how far away are you from the host star. And if we look particularly in the gray region, which are planets that are too close to their star to have formed there, but they're a little further away than the hot Jupiters, so they haven't experienced so many tidal circularizations, you can see how the blue circles are filling the whole plot, but the red squares are confined to the very top of the plot. What this is showing us is that the more metal-rich stars have planets with a range of eccentricities, whereas the more metal-poor stars, the planets are confined to low eccentricities. You can also see that in the histogram, how the red one, those are at low eccentricities. So the interpretation here is that in order to get inside 1AU, the planet had to experience either disk migration or scattering with the other planet, and that only in the system with the more metal-rich stars and a bunch of planets do you have the planet interactions that lead to high eccentricities. The other result I want to show you relates to the fact that Kepler found too few hot Jupiters. So before Kepler was launched, people found hot Jupiters using other approaches, mostly what's called the Doppler approach, and they found a certain rate of hot Jupiters. But then when the Kepler spacecraft searched for these close and giant planets, it only found 1/3 as many as you would have expected. So it's been a big mystery why the Kepler mission found so few hot Jupiters in its sample. And this is really interesting because it seems to imply that hot Jupiters are related to the sample that you're looking at, which tells us something about how they might be produced. As was argued in this paper that's explaining this discrepancy, if you saw a difference in the hot Jupiter rate among different types of stars, that might tell you something about how hot Jupiters are formed. So to show you here is how many transiting planets that we see as a function of orbital period. And the red are the Kepler Jupiters, and then the gray and black is what we would expect if Kepler was seeing, if the stars that were found in the other surveys had the same planet population as in the Kepler survey. So you'd expect the black dash and the red to be exactly the same if there's the same type of planets around stars in the Kepler survey as there are around other types of stars. But instead, at short orbital periods, they look really different. This is just another showing how the Kepler survey is missing hot Jupiters. You'd expect there to be a lot of hot Jupiters because they're so close to the star that it makes it really likely that you'll see them pass between you and the star. But instead, they're missing. Okay, so I have emphasized this. And so my hypothesis was that if there really are two ways to form hot Jupiters that depends on the metallicity of the host star, if you take the Kepler stars and break them up into the metal-rich stars and to the metal-poor stars, then maybe you'll see a difference. It's been well known that the stars in the Kepler sample are a lot more metal-poor than the stars that were observed from the ground. So maybe the reason that we're missing the hot Jupiters is that we're not looking around the same type of stars where you can form a lot of planets and have this hot Jupiters formed by high eccentricity migration. So this is what happens when I break up the sample. In the top is the full sample, in the middle is the more metal-rich Kepler stars, and in the bottom is the more metal-poor Kepler stars. And you can see that around the more metal-rich stars, we recover this pileup of short-period Jupiters that was missing in the overall sample. So the message I want you to take home from this little segment of the talk is that planets orbiting metal-rich stars show signatures of planet-planet interactions. So the interpretation for this is that these are the type of stars that have an abundance of giant planets that can lead to these strong gravitational interactions. Whereas around the more metal-poor star, if you just have one Jupiter, the only way for it to move around is through this gentle disk migration. So now I'd like to step away from extrasolar planets and go back to our own solar system, because we actually have some of the same questions about what happened in our solar system as we do about what happened in extrasolar systems. In particular, we have the same question about planet migration for Neptune. Did it have a gentle migration or did it have a violent migration? Some people thought that Neptune migrated very smoothly through a disk of comets and asteroids, planetesimal disk, and it just moves along on a circular orbit to get from where Neptune formed actually a lot closer to the sun to where we observe Neptune today. So this is sort of an analogy to the disk migration we were talking about earlier. But other people have proposed that all the giant planets in our solar system started out packed much closer together, then they scattered each other, and Neptune got kicked out to its distant orbit that we see today. So both of these theories deliver Neptune at where we observe it today, but one of them has a gentle migration and one has a more violent migration. And both of these theories can produce an object like Pluto on its very strange orbit. So we want to take a look at some of Pluto's friends. Even though it's no longer a planet, it has a bunch of other small bodies called Kuiper belt objects that whatever happened in the solar system, they have recorded that history, and we can use it to try to reconstruct whether our own solar system had a gentle or violent history. To motivate why it might be possible to do this, I want to show you, though, one example from a Kuiper belt that's orbiting another star. This is the Beta Pictoris system. I showed you this picture a little bit earlier in the talk. And again, we're looking at a disk edge on, and instead of being flat, the disk has a warp in it. Let me show you a movie we made of how this warp happens. This seems to be working. Okay, yeah, the movie isn't working, but what you would see is that the disk would start out as flat, but then it would slowly get warped to look like the observation. And actually, no, it's still not working. So all this is meant to show you is that planets can have a strong effect on their debris disks, and we can see, like, this disk is evidence for a planet on an inclined orbit causing this warp, and that the planets in the solar system could have done the same thing to the objects in our Kuiper belt. So now let me show you some observational evidence from the Kuiper belt that's sort of the equivalent of this warp that you see in this disk. So these are a bunch of Kuiper belt objects, and I'm plotting their eccentricity versus semi-major axis. So on the bottom plot is how far away are you from the sun, and on the top axis is on the bottom you have a very circular orbit, and on the top you have an eccentric orbit. So we interpret the objects with the eccentric orbits as gotten stirred up during whatever our own giant planets are doing. And we can see that there are two populations in the Kuiper belt. The red ones, which I'm making red because they're actually redder in color, are confined to low eccentricity, so this is a very quiet population. But then these blue ones have a big range of eccentricity, so these ones are all stirred up. And here's just showing you these ones confined, these ones are stirred up. So this is a mystery because how did these ones get so stirred up, whereas the red ones are so quiet and it look like they haven't been disturbed at all? And this is a challenge if you have something happening to our giant planets, because how in particular is Neptune supposed to stir up these ones while leaving these ones all quiet and undisturbed? So the hypothesis that people have is that those red ones just formed where we observed them, but these stirred up ones started out closer to the sun and then got scattered in. So the takeaway concept from this plot is that there are two distinct populations, and that our planet Neptune, whatever history that it underwent that we're trying to figure out, needed to deliver those ones, scatter them in without stirring up those ones. So that actually imposes a big constraint on what could have happened to Neptune in our solar system. As it's moving around or getting either smoothly or by getting scattered, it needs to at the same time be moving those blue Kuiper belt objects into a different part of the disk without stirring up the red ones. So let me show you a movie in which this successfully happens. So we can see on the bottom, the yellow bar is the red ones can't go above that level in that region. And you can see that the red ones are getting a little stirred up, but they haven't quite reached that yellow bar. Let me show you again. This time I want you to watch the blue objects. Those ones are getting scattered in from a different distance, and they need to go, they need to be low enough so that they stay inside the region. So this is an example where Neptune does successfully bring in these blue objects without too much stirring up the red ones. So what sort of dynamical history does that imply for Neptune? Does this mean that it moved out smoothly, or did it have to get kicked out by the other planets? We can actually turn these requirements into a map of requirements for Neptune, where it could have been and how eccentric its orbit could have been. So here's a plot of, on the bottom is Neptune's distance from the sun. At the edge is where it is today. And on the y-axis is how eccentric is Neptune's orbit. If it just moved out smoothly, we'd expect it to always be at the bottom of this plot. But if it got kicked around by other planets, then it may sometimes be at the top of the plot too. And the purple is where I'm saying this is not the region where Neptune can scatter in those blue objects that we saw. So Neptune needed to spend some time not in this purple part, so it needs to sometimes have been up on the top right corner of the plot. So this is interesting because it's showing that Neptune does need to have had an eccentric orbit in the past. So it can't just have had this nice, happy, smooth history. It needed to be kicked around a bit by the other planets. However, it can't spend too much time up here because then it would have stirred up those red objects that we saw. So it either needs to have its eccentricity damp back to circular really quickly or to precess really quickly. So let's see an example of this. Maybe Neptune gets kicked by Jupiter up to here, then it quickly circularizes, and then it smoothly moves from here out to where we observe it today. The takeaway here is that Neptune needed to have a high eccentricity in the past to have scattered in those objects, so it needs something bad and violent to have happened, but it also needs to undergone a period of smooth circular migration. So if we go back to that question that we started out with, is the assembly of planetary systems typically a gentle or violent process? We can now say that if we were to look inside this instruction booklet, we'd see both of those as different options. With the hot Jupiters, we're finding evidence that maybe both of those methods can lead to hot Jupiters. And even in our own solar system, we're seeing that maybe in one system, which is ours, that both gentle and violent processes were at work. So now I'm going to take the last 5 minutes or so to talk about why this is so important, which is, first of all, it's just intellectually interesting, and you want to know what happened in our solar system, what happened in other solar systems. But even if you don't really care about giant planets and you only care about planets like ours, you should still really care about what the giant planets are doing. So as an example, these are all the candidates that were found by the Kepler mission. On the x-axis is the orbital period, on the y-axis is the size. Most of them are really small. So you might think that what I talked about doesn't really affect them because I was only talking about giant planets. But these planets are often in the system with a giant planet, and they really care about what the giant planet did. The Kepler spacecraft may only see the close-in small planet and not know about the giant planets that are there. So it's really important for us to get a feel for what sort of giant planet histories are common in order to better interpret what possibilities there were for every planet to undergo during its lifetime. So let me show you an example of how giant planets interacting with each other can cause bad effects of small planets. So if you think about our own solar system, we have these small planets close in, and we have these giant planets that are further out. And what would have happened if our giant planets had a sufficiently strong gravitational interaction? Here's a movie by Sean Raymond. So the big black circles are the giant planets, and inside them are some smaller planets that have formed. And you can see that the smaller planets are getting a little bit stirred up out of their plane, but for now the small planets are sticking around, the giant planets are too. But now I want you to concentrate on these small planets and see what happens to them when the giant planets start kicking each other around more strongly. So they're getting very excited and stirred up. And so now it's sort of like our own solar system where things got stirred up a bit, but not too much. But if we keep watching, oh no, now they're all gone. So the giant planets are still there, and eventually they'll settle down, and we'll see something like a lot of the extrasolar systems we see, where two giant planets, one of them that on a very eccentric orbit. And so you can see that even though the giant planets may not even be anywhere near the small planets, they can really strongly affect their histories. Okay, and then last I'd like to show you as a more metaphorical analogy for this, a clip from the first Hobbit movie where I think we saw something similar going on. So we have the Hobbit, and it's on this mountain, and there's all these rocks falling. The Hobbit is wondering, like, what's going on? Terrible things. And then you realize that they're not on a mountain. They're on two giants that are at war with each other and that are violently interacting. So the same thing can happen in a solar system if the Hobbit is the small planet and the giants are the giant planets. So whether you care about the giants or the hobbits, you still need to know what happened to the giant planets in the system and what sort of dynamical histories are common for giant planets. Thank you very much.
If you could put your hand up if you've got a question. I'm going to ask the first one, Rebekah. Firstly, Socrates, I was really shocked to see that he's still publishing.
Oh, because he's from ancient Greece.
Right, I thought he'd been done away with by the tyrants or something like that. But he was saying that that was how you were getting the 5 hot Jupiters, the hot super eccentric Jupiters. Can you tell us a little bit more about how they were
how they arrived at
suggesting,
that prediction? Yes. I have a little cartoon about this that I can show you. Let me skim. Okay. So the planet starts out on this highly eccentric orbit, and then this is a cartoon where it gets more circular as it moves up the plot. So we can just imagine the planet, like I showed before, getting more and more circular. So if this is what's happening, then there should be Jupiters all along this track on different stages of the migration. So what Socrates and collaborators did, actually his first name's Aristotle, to go with the first part of your question. They took the number of planets observed to have these moderate eccentricities, and then they know how long does it take to move along the different parts of the track. And based on that, they predicted how many of these super eccentric Jupiters should be. So that's where the prediction is based on.
That and the music of the spheres or something like that. Perhaps he was talking to Pythagoras. Or is Pythagoras his middle name?
Yeah, who knows who the et al. Are. Maybe they're other philosophers.
Right. Questions over here? I know we had a couple.
Yes. What evidence do we have that Neptune that it formed much closer to the sun than its present orbit? And how about the other giant planets in our solar system? Did they form where they are now, or do we have evidence that they migrated too?
Great question. So there's sort of 2 lines of thinking for that. One is that that's the best way to explain the strange orbits that we see of objects in the Kuiper belt. Besides the type of objects I mentioned, there are objects like Pluto that they're in what's called an orbital resonance, so they have an integer ratio of their orbital period. So every time Neptune goes around the sun 3 times, Pluto goes around the sun 2 times. So all the theories for getting this sort of special configuration for these Kuiper belt objects are based on Neptune undergoing migration. The other argument is that the time scale for forming planets depends on how far you are from the sun. So people think that out where Neptune is, you'd expect it to take too long to form Neptune. But that's a more theoretically based prediction, whereas the other one is more trying to explain observations. But yeah, most of the current theories have all 4 planets starting out. Neptune is at about its spot, but the other 3 giant planets being a lot closer to it. So they're all packed close together. And then they either smoothly migrate out or they start scattering each other.
Becky, the models I've seen for the Plutinos require many of them to be captured around when Neptune was at 24, 22 AU, and then gradually migrate out. But you have an epoch where Neptune is at 26 or so AU and fairly eccentric. Does it have to go to that epoch and excite the disk and then come in and get calm and then go out, or can it keep the Plutos and get the right distribution of eccentricities if it's that eccentric when it's that far away?
Yeah, that's a great question. So Plutinos are like other objects that have orbits very similar to Pluto. That's why you shouldn't feel too sorry for Pluto for not being a planet anymore, because it has all these friends. And people had argued that you need, to get their orbits right, you need Neptune to migrate a long distance. But people have claimed to be able to get the right eccentricities also by scattering all the objects in and catching things into resonance that way. And then in some of the models that I've done, there's yet another way to get them into resonance, which is that things are scattered in, and then what's called a secular evolution time is a lot closer near resonance, so you can draw down a lot more things near the resonance. And my understanding is that the population of Plutinos is not yet quite large enough to be able to distinguish between any of those ways of catching them to resonance. But maybe once we have LSST or something with a bigger population, you could actually use the eccentricities and what's called the libration amplitudes to really pin down which of those models must be right. But at the moment, it's sort of a toss-up between all the models.
Hi. You've described and emphasized the tidal circularization origin for the hot Jupiters.
Mm-hmm.
Now, I'm sure there are other theories, and I just wonder how far in could you actually form planet as massive as the hot Jupiters in other theories like disk fragmentation or I mean gravitational instability?
Yeah, great question. So, yeah, I talked both about the tidal circularization and the disk migration. Those are the two main theories for getting it so close. But what you're asking about is where do you form the giant planets? And traditionally, if we assume that all disks that planets form from look like in our solar system, it needs to be like beyond the orbit of Earth, whether it forms by fragmenting from gravitational instability or from what's called core accretion that I talked about, where you start out with a giant core and accrete a bunch of gas. However, Kepler is finding all these small planets that are really close to their star. Some of them are as big as a Jupiter's core. So that started to lead some people to think that maybe other disks that planets form from have a lot more solids located closer to their star. And in that case, it's not as clear that you can't form a hot Jupiter closer in. But no one has yet convincingly demonstrated that you can form a Jupiter closer in than a couple AU. Generally, people think it's beyond a couple AU, but that's sort of an open area of research.
Okay, I have a question about disk migration. I have trouble understanding how after big giant gas planets are formed, there's enough left over to actually, in the disk, to actually slow these very big planets down.
Oh yeah, that's a good question. It's because the material that is slowing the planet down, as you put it, or causing it to migrate, does not have to be the material that's nearby the planet. So the planet forms, and it forms out of some ring of material, but the stuff that isn't in the ring is still affecting its migration quite a lot. And in fact, the strongest effect comes from parts of the disk that are near these orbital resonances that I mentioned. So if you're a Jupiter and you look at where the disk is orbiting twice as slow as you are, that's actually what's contributing the most to your migration. So it's really the other parts of the disk that didn't go into forming you that can cause you to migrate quite a lot.
Yeah. Why doesn't core accretion work if you just start with hot silicates at the silicate line?
Oh, why? I see. You're saying why can't you form the core from material that isn't solid, from evaporated?
Solid silicates.
From solid silicates instead of ices. It's all a matter. The only argument is based on the surface density. People don't think there's a high enough surface density of solids that close in. And if you change that assumption, then arguably you could form something there.
Any other questions?
When one of these Jupiter starts migrating in through the the slow method, obviously friction knocks down the angular momentum to some extent, so it doesn't have as much when it gets in closer, right?
It's I guess you can sort of think of it as friction, but it's not exactly friction. It's more just that you're giving all your angular momentum to the disk and getting rid of it yourself. Yeah.
Right. So I guess there must be cases where the planet just rolls right into the star.
Yeah. So people have debated if migration is so efficient, why doesn't the planet just hit the star, as you say? And that's actually somewhat of a challenge for disk migration. Some people think maybe the disk is truncated, so you stop at the inner edge of the disk. Or that even magnetic fields may play a role, but that is definitely an open question. And also, even with the tidal migration, why don't you just hit the star? Did we lose a bunch of Jupiters? It's still, yeah, people are thinking about this.
All right, if there's no further questions, Becky, we have a special SETI.org/talks mug for you.
Oh, this is so nice.
Yeah, it's got some robots talking, no doubt about the next Hobbit movie or something like that, or maybe even the Drake equation, I think it is. But not to worry. Please join me in thanking Becky for a great job. If you have any more questions, please come up and talk to her now.
Oh, yeah,
Just
thanks
have
for
another
coming.
question.
Yeah,
This general migration.
I'm just going to turn this off so that, yeah.